today we will keep going with chapter 5 since we are replacing our normal workday of problem working on Friday with the quiz. We're going to do some problem working today. So I'm going to set up the problem, give you time to work on it, and then I will go over how to do it. These are in chapter 5. Make sure that you are doing your chapter 5 reading and understanding the concepts. We have our next exam on April 9th. So you still have a little while, but just make sure you don't get too far behind. All right, so I'm going to set up the problem and then we are going to try to work it yourself. This question is similar to the problem I worked on Monday, so it would probably be helpful to have your notes out. And for this question, I am going to help you by setting up the assumptions that are there, which is one of the harder parts. All right. Get that, get the chat open. Okay, so this is problem 512. And in this problem, we have a rigid insulated tank that is initially evacuated. A rigid insulated tank that is initially evacuated, meaning it was in a vacuum, that is initially evacuated, is connected through a valve to a supply line, is connected through a valve to a supply line that carries steam at 1 megapascal and 300 degrees Celsius. That carries steam at 1 megapascal and 300 degrees Celsius. Now the valve is open and steam is allowed to flow slowly into the tank. Now the valve is opened and steam is allowed to flow slowly into the tank until the pressure reaches 1 megapascal, at which point the valve is closed. Until the pressure reaches 1 megapascal, at which point the valve is closed. Determine the final temperature of the steam in the tank. Determine the final temperature of the steam in the tank. A rigid insulated tank that is initially evacuated is connected through a valve to a supply line that carries steam at 1 megapascal and 300 degrees Celsius. Now the valve is opened and steam is allowed to flow slowly into the tank until the pressure reaches 1 megapascal, at which point the valve is closed. Determine the final temperature of the steam in the tank. Okay, so we have some sort of supply line that is pulling in steam to a rigid tank. So we have some sort of tank. This tank is actually going to be our control volume. And we have steam that's coming in through the supply line that at first is, the valve is closed, then the valve is open. This is just like a really rough schematic of a valve. The steam is coming in at 1 megapascal and 300 degrees Celsius. This tank is our control volume. We know that the pressure at 0.2 is the pressure that is coming in, which is our 1 megapascal. Right? So we have steam at 1 megapascal, the valve is open and steam is allowed to flow into the tank until the pressure reaches 1 megapascal. And then we have the temperature that's coming in the supply line is 300 degrees Celsius. We know the tank is rigid, so there's no going to be boundary work, there's no piston, there's nothing happening there. So the assumptions that we need to make, what are some assumptions? Use the chat. What are some assumptions that we can make to set up this problem? Okay, here's a hint at one assumption. The tank is initially evacuated. So what does this mean in terms of assumptions?
It's empty.
So right, there's no initial temperature or pressure in the tank. There's also, it's totally evacuated. So Emma, you're kind of close. The volume of the tank it's a rigid tank. It's going to stay the same, but there's no air in here. There's no mass in here. So our mass at 0.1 is going to be 0 because we're initially evacuated. We also don't have any real initial pressure or temperature in the tank at the starting conditions because it was totally evacuated. This is like a completely empty tank. And then Dan also said that our potential energy and kinetic energy are going to be roughly equal to 0. So there's no velocity that's really playing a part, no change in velocity, there's no change in gravity. We also have our specific kinetic and potential energy of the tank are going to be 0, and then our overall energy of our system are still going to have a kinetic and potential energy of 0. So we haven't really worked a case where these aren't equal to 0, except for the problem that we work with the nozzle. So when you do have a nozzle change, that's when we have that velocity change that was significant. All right. So one of the other things that we have here, a rigid insulated tank. So what assumption does that lead us to?
No exchange in temperature.
I'm not sure that we get that assumption from the fact that it's a rigid insulated tank. Yeah, so Justin, yeah, so rigid meaning that there's no movement, there's not going to be any real work that's being done, there's no piston, there's no additional work that's coming in from a shaft or a turbine or anything. So we can approximate that the work is 0. And this is because we have a rigid tank. So there's no boundary work, there's no piston. There's also nothing that's in here about electrical work or turbine, shaft work, anything. And then insulated tank is telling us that it's going to be roughly adiabatic. We're going to have no exchange of heat. So this is given to us by the word insulated. So one of the other things here, we have one supply line that's coming in at one point to this one tank. So we have one inlet for mass flow, one inlet. So mass in is coming in that one inlet, this single inlet here. And then we have no outlets, no exits. So our mass flow out equals 0. Finally, I kind of already said this over here. We're assuming that our control volume is our tank. And lastly, is this a steady flow process or is this an unsteady flow process? So if you say steady and I shake my head, then it's probably a good guess that it's unsteady. So remember our steady flow processes were nozzles and diffusers, throttling valves, pipe and duct flow, turbines, compressors, and there's nothing about a tank, right? A rigid tank. And this isn't a throttling valve. This is just a valve to open a supply line. So this isn't a throttled system. And we know that when you first open this valve, right, to a totally evacuated tank, it's going to quickly rush in. And then as it starts to come up to about an equal pressure, that pressure is going to be slower. Or that supply line input is going to be slower. So we don't have this steady, steady in, steady out, steady in, steady out, like we do for steady flow systems. Also, for this class, because this is not a super advanced level thermodynamics class, I'm not going to ask you a steady flow question without it being a steady flow device. So if this was a steady flow question, this device would be a steady flow device. So it would be a diffuser or a throttling valve or a pipe and duct flow. So if you don't see that, especially for this class, you can assume that it's unsteady flow. So this is unsteady flow, but what assumption do we make about unsteady flow to allow us to look at the different properties? So what do we call the flow? That's an assumption that we're making about the flow. Yes. Yeah. Good job, Layla and Dan. So uniform flow. So we're assuming this is a uniform, uniflow. I shortened it. Uniform flow. I hear somebody like jostling around. Just make sure you're on mute, please. I can't see who it is.
Oh, sorry. Just asking, would we always be given like the picture, like the rigid tank, for instance, or would we always have to draw it out and like know instantly, like what to draw?
For a problem like this, I would expect you to know how to draw a rigid tank with a supply line because it's pretty simple. For something that's a bit more complicated, I might give you the picture, but typically you should know how to draw, a diffuser, a tank, a throttling valve. You should know how to like do a sketch of those. So I wouldn't rely on getting a picture for the problems. Other questions?
Are you going to tell us whether or not it's unsteady flow?
Am I going to tell you when you're not at steady flow?
Yeah, steady or unsteady flow.
No, that's something that you need to know. So that's why I'm trying to point it out in these questions. Like steady flow devices is when you assume steady flow. If you don't have a steady flow device and you think about the problem, you should be able to assume that it's an unsteady flow device. So that's kind of what I'm trying to make sure that you're understanding. Okay, so it's 11:48. I'm going to have you work this problem. As I mentioned before, this is pretty similar to the problem I worked on Monday. So having your notes from Monday will help you. I'm going to let you work this for about 10 minutes and ask me any questions that come up either in the chat or you can say them out loud. And then I'm going to go over the solution. So Yep, 10 minutes. So probably at about noon, I'll start going over it. All right, I'm gonna start going over it, but if you would like a couple more minutes, just type in the chat. I can give you more time, but I don't want you to just sit there and flounder either. So just let me know if you want more time or not. When I spoke, I like startled Beefy, who was snoring so loudly. He's like mad. Okay, so anybody need more time? Just let me know in the chat if you'd like a little more time to try to solve it yourself. Okay, then I'm going to go ahead and solve this. So first, for these problems, for unsteady flow, we're always going to start with our mass balance and our energy balance, unless we're only looking at mass balance. But typically the way we always do it, start with the mass balance, then go to an energy balance. So our mass balance equation is going to be the change in mass of our system is equal to the mass coming in minus the mass going out. And remember, the change in mass of the system is M2 minus M1 is equal to M in minus M out. So this is the mass of the system. The assumptions that we made here were that we have no mass at our starting evacuated system, right? It was evacuated, it was totally empty, there was nothing in there, it was existing in a vacuum. So there was no mass coming in. We also have no exits, we only have an inlet, so our mass coming out was 0. These were assumptions we made in the setup of the problem. So therefore, our mass balance becomes our mass at our final state, our second state, is equal to the mass coming in, which makes sense, right? We have a rigid closed tank that's getting mass from a supply line. So whatever that mass is coming in is going to be the mass that we end up with, right? So logically, that makes sense. There's our mass balance. Our energy balance is going to be a parallel equation where we have the change in energy of our system is going to equal to the energy coming in minus the energy going out. And the energy of our system here is M2 specific energy 2 minus M1 specific energy 1, our final and initial state. And these are equal to our Q in plus work in plus the summation of all incoming mass times fluid flow energy minus Q out plus work out plus the summation of our outgoing mass times our fluid energy, fluid flow terms. All right, so using the chat, what all cancels from this equation?
M1.
Mm-hmm. Yep.
And work and energy, heat transfer.
Right. So everything you said is correct. Hopefully you're getting all of these. You working at home already kind of know what I'm going after. This is an insulated tank, so we have no heat exchange that's happening. We made that an assumption that Q is roughly 0. We have no work coming in or work going out. We don't have any shafts. We don't have any piston work. We don't have anything. We assume that work is 0. We don't have any mass going out because we don't have any exits. So this whole term drops out. We don't have any mass at our initial point, M1, right? So this whole term drops out. And we do have some incoming mass, and we do have some mass at point 2. So while our kinetic and potential energies are going to cancel out of this specific energy and fluid flow energy term, that we'll do that in the next step, but those are other things that cancel. So our equation becomes M2E2 is equal to the summation of incoming mass times fluid flow. So for this problem, we have one inlet. So all of our mass coming in is coming from that one inlet. So therefore we could make this into M2E2 is equal to Mn times our fluid flow term, our fluid flow energy term. Okay, so then converting the specific energy and this fluid flow energy into their full broken up equations, we have M2 times specific kinetic energy at point 2 plus our potential energy at point 2 plus our internal energy at point 2 is equal to our mass coming in times our change in kinetic energy of our system plus the change in potential energy of our system plus the change in internal energy. These are still lowercase. Plus the change in internal energy of our system plus pressure times specific volume. We know that kinetic and potential energies are going to cancel across the board here. And so we are left with the equation M2U2 is equal to Mn times U plus P specific volume, which we know that this becomes enthalpy. So therefore, M2U2 is equal to Mn times Hn.
I didn't think that internal energy was included in the theta equation on the right-hand side.
You didn't think internal energy was included in this equation?
I thought it was just our specific volume times like a height, like GZ. Maybe I'm wrong, like for fluid flow.
So our kinetic energy term is that 1/2 velocity squared. Our potential energy term is that gravity times height term. And then our internal energy, it has always been there. So for our fluid flow term, we have always had these 3 units. These are associated with our fluid energy. And then this last term here is associated with the energy of flowing fluid.
Okay.
So we've always
So-
had these 3 grouped together, kinetic, potential, and internal energy. They're going to be in every energy equation like together. We're just adding this additional term that's associated with flowing fluid. We added that in chapter 4.
Okay, so when we refer to theta in this equation, then it includes all 4 of those specific terms.
Right.
Okay, got it. Thank you.
Yeah. Other questions? Kind of following in the same vein, I think that this chapter in particular has a really nice blue summary section at the end. So at the very end of chapter 5, the summary on page 251 in the 8th edition, I think it's like 248 in the 9th edition, is really nice at breaking down all of the equations that you know so far. So it's mass balance equations, mass flow rate, different things, volumetric flow rate, energy flow terms, energy equations, all of these different fluid equations. It has them on one page. So I think it's actually pretty nice, like in terms of kind of cohesively, concisely laying it out. If you have time, like make a scan of it, use that as a study tool. I think it's really helpful. Okay, so now we're here. M2U2 equals MNHN. Let's keep in mind, like, what are we looking for in this problem? So we're looking for the final temperature of steam in the tank. So to go from here, where is temperature hiding in this equation? Like, how can we get temperature from here? And it's a little confusing, right? Because there's so many ways to go from here. Like, should you convert to MC delta T? Should you convert to, ideal gas equation? Should you go to the property tables? Like, what should you really do? So one of the things that helps is to now plug in your mass balance equation to see where that takes you. So unlike some of the other problems we've done where we can now just go to NC delta T, for these problems, you have to go back to using your mass balance equation up here. So our mass balance equation tells us that M2 and Mn are equal. So this equation becomes MU2 is equal to MHN, which means that this mass actually cancels from both sides. So now our equation is U2 equals HN. And so now our equation, this is continued, is U2 is equal to HN. And we want to try to figure out temperature. So when we go back and look at like what is told to us in this problem, we have pressure at our ending point and our incoming point, and we have temperature at our incoming point. So we have our pressure at our incoming point, and we have temperature at our incoming point, which allows us to go to the property table and look up our enthalpy value at our incoming point. We also have pressure at our point 2. And once we get this enthalpy at our incoming point, we now have our internal energy at point 2. And we know from the property tables, we need 2 values to fix our state. So in order to look up something from the property tables, we need to know either its phase and something else about it, or we need to know these two aspects to fix this point, right? So pressure and temperature, we can look up the enthalpy. And then for the second part, we have pressure and internal energy. We can look up the temperature at point 2. So for this problem, we have our pressure at our incoming is 1 megapascal. And we have our temperature incoming is 300 degrees Celsius. So when we go to the tables in the back of the book, we can see when we start at table A5, and we look at our pressure of 1 megapascal, which is 1,000 kilopascal, our saturation temperature is 179 degrees Celsius. So therefore, our temperature is greater than our Tsat, which means that we are a superheated vapor, and we need to use table A6. So when we go to table A6 at 1 megapascal, and I can look up my H value, my internal energy value at 300 degrees Celsius, I get 3051.6 kilojoules per kilogram. And I know that my HN value is equal to 3051.6 kilojoules per kilogram. And my HN value equals my U2, which means my U2 value is equal to 3051.6 kilojoules per kilogram. Sorry, I don't think I wrote kilogram here. Kilogram. So when I go to fix my, I fixed my incoming properties. Now I'm going to fix my final state properties. My pressure at point 2 is going to be this 1 megapascal. And my internal energy at point 2 is going to be equal to, using this equation, equal to my enthalpy that's incoming, which is 3051.6 kilojoules per kilogram. I don't know why I did this. So therefore, using table A6 still, we have steam that's coming in, it's filling it up, we're not really changing state. We have our 1 megapascal. I'm looking for my internal energy of 3051. And this is between 2,957.9 and 3,125.0 at the temperatures of 400 and 500 degrees Celsius. So this problem would have you interpolate, but we have 29 and 31. So it's fair to say that at about 400 degrees Celsius, we're going to have about 300,000 degrees or 300,000 kilojoules per kilogram, right? Just taking the halfway point between these. So I would just approximate this T2 to be 400 degrees, 450 degrees Celsius. If you wanted to do interpolation, T2 is going to be 456.1 degrees Celsius. Phoebe, I'm trying to teach you. Thank you. All right. So when you're given things like pressure and volume and temperature, that's when you're gonna kind of be thinking about the ideal gas law. But for this problem, we weren't given any information about volume, which makes it tricky. And I didn't give you the R value, which I typically always give you the R value for problems if you're gonna need the ideal gas law. For MC delta T, we don't know our starting temperature. We could assume that it would be 0 because it was in a vacuum. But typically, if you have 2 points to fix something, it's always going to be easier to use the property tables. So since we were given pressure and temperature coming in, it makes sense to try to use the property tables. Honestly, just practicing these problems, you get a little more comfortable with like working it out past like this point, because this gets confusing. Okay, well, I can maybe get to here, but then what do I do? And sometimes it's just kind of messing around and seeing where you get stuck, going back and trying another approach. But a lot of it's also just practice.
So just to make sure, like, so we can use like the PV equals MRT, like the ideal gas law. It's just like we just have to find the R ourselves.
For this problem, no, you couldn't use the ideal gas law because you aren't given any information about the volume of the tank.
Oh, yeah.
And then I typically, as a hint, when you're supposed to use the ideal gas law, I typically give you the gas constant just to like give you a hint about it. But for this problem, you don't have enough information to use the ideal gas law effectively. And also, none of these are in the ideal gas law like equation. So it's not really going to work for this one. So Noah, I didn't, okay, so for this problem, you're supposed to interpolate, right? We have 400 degrees at 29,000 and 500 degrees at 31,000. I'm sorry, 3,100. And so you have to interpolate to figure out where in between here you get 3,051.6 kilojoules per kilogram. But I haven't asked you to interpolate it on an exam, and I'm not going to. So I would probably give you a value that's exactly lined up. But for this problem, you're supposed to interpolate. I didn't want to go through interpolation. It takes too much time. So I just roughly approximated 450 degrees Celsius, but I gave you the answer if you were to interpolate. So this is an approximation, and this is an interpolation. So this is the exact answer, and this is what you can guess it to be, right? We're about halfway between these 2 points. Okay, so I'm gonna do another problem. Well, I'm gonna set up another problem for you to do. This one's a little bit shorter. So this is problem 5140. It's one of the FE style questions in the back of the book. A steam turbine operates with 1.6 megapascal and 350 degrees Celsius of steam. A steam turbine operates with 1.6 megapascal and 350 degrees Celsius of steam at its inlet, and saturated vapor at 30 degrees Celsius at its exit. And saturated vapor at 30 degrees Celsius at its exit. The mass flow rate of steam is 22 kilograms per second. The mass flow rate of steam is 22 kilograms per second. The turbines produce 12,350 kilowatts of power. The turbines produce, 12,350 kilowatts of power. Determine the rate at which heat is lost through the casing of the turbine. Determine the rate at which heat is lost through the casing of the turbine. Through the casing of the turbine. All right, so I'm going to give you a few minutes to work on this, and then we'll go over it, probably like 6 minutes. All right, just in the interest of time, and I have one more problem I want to work after this, I'm going to go ahead and start reviewing. Is there anybody who would really like more time? All right. Okay, so for this problem, we're looking at a steam turbine, which is great because it is a steady flow system. So we have a steam turbine. A lot of times they look like this. They have like a bunch of baffles in here. It's not a good drawing. It's like what's on the front of your book, right? So a turbine, but we kind of just model it as this almost diffuser type shape where we have an incoming stream at one end, we have an outgoing stream at the other end, and then we have some sort of shaft that is being spun here to produce work. So we have a turbine, we have our work out here. This work out is 12,350 kilowatts. We have some heat that is coming out. We are told determine the rate of heat that is lost through the casing of the turbine. So we are assuming that our turbine is our control volume and we are losing heat from the casing of the turbine. We have some incoming steam and some outgoing saturated vapor. So we know at incoming here, we have steam, which we don't know for sure if this is saturated vapor steam or steam, but they probably would have called it saturated vapor if that's what was coming in. So it's probably superheated steam, but we don't know for sure. But anyways, the steam is coming in at a pressure of 1.6 kilopascal. Nope, megapascal. 1.6 megapascal. And 350 degrees Celsius. And it is coming out at 30 degrees Celsius, which makes sense that we would be losing heat, not gaining heat, because the steam is being used to produce this shaft work. And we know that we are coming out as a saturated vapor. So so we know that this is a saturated vapor. What is the quality of a saturated vapor? The other way around. Yes, one. Good job. You are guessing 50% today, and it's funny. Okay, so we have remember our quality is going to be our mass of our vapor over our mass total. So if we have 100% of a saturated vapor, our quality is 1. If we have 100% saturated liquid, our quality is 0. But so we know our quality at 0.2 is 0, or we know that we can be looking at our variables with the subscript of G. So we're at a saturated vapor coming out of here. Okay, so for steady flow systems, we have things like nozzles, diffusers, turbines, other steady flow systems that we've been through. So for this problem, we can assume that this is a steady flow system because we have a turbine. We can also assume that kinetic energy and potential energy are roughly 0 because we don't have any gravity or velocity major changes. So there are our assumptions. For our unsteady flow, our uniform flow systems, we start by doing a mass balance and an energy balance. For our steady flow systems, we don't necessarily need to do that because we don't have the same complicated mass system. And a lot of times with single flow incompressible fluid systems, the mass balance is really easy. So a lot of times here, we just go ahead and start with the energy balance, unlike the unsteady flow systems. So we have energy balance, which is the change in energy of our system is equal to energy in minus energy out. For this problem, we're asked to determine the rate that the heat is lost, and we are told information about mass flow rate. So for this problem, we are working with a component of time. So I'm going to add my time here, my dt. And since this is a steady flow system, we are very lucky that we can cancel this out, which means our equation becomes our energy in over time is equal to our energy out over time. My dog's about to bark his fool head off. Hold on. Okay, thank you. Sorry, that's a downside of teaching from home. Sorry, the Amazon guy came in. He's here to kill us, evidently. All right, so we have our energy in is equal to our energy out. Now we can just plug these in with our what we know for our energy equations. So we know our energy in is the our Q over time that's coming in, plus our work over time that's coming in, plus the summation of all of our incoming mass flow rate times our fluid flow term is equal to our Q coming out plus our work coming out over time plus the summation of our outgoing mass flow rate times our fluid flow energy term. So we don't have any heat coming in. We really only have heat that's going out. And we don't have any work that's coming in. We only have work that's going out. And our kinetic and potential energies can cancel from here, which these are going to convert into, these fluid flow terms are going to convert into enthalpies. Because we're canceling our kinetic energy and potential energy, we're left with internal energy plus pressure times specific volume, which we're just converting into enthalpy, right? Because enthalpy is U plus P specific volume, and these are all specific. So therefore, our equation becomes our mass flow rate at 0.1 times our enthalpy at 0.1 is equal to our mass flow rate at 0.2 times our enthalpy at 0.2 plus our heat over time coming out, plus our work over time coming out. I know, BB. Really. He's like very concerned that, you know, things are happening? He's like over here leaning against me, trying to get up on the chair. Ugh. Thank you, Emma. All right. So now we have this equation. Our mass flow rate at 0.1 times our enthalpy at 0.1 is equal to our mass flow rate at 0.2 times our enthalpy at 0.2 plus our work over time coming out. I'm sorry, heat over time coming out plus our work over time coming out. All right. So for this problem, we are solving for the heat that's being lost through the casing of the turbine. So when we isolate for this term, our heat over time that's coming out through the casing of the turbine, we get our mass flow rate at 0.1 H1 plus UBT minus our mass flow rate at 0.2 H2 minus our work over time that's coming out. So I moved this term and this term over to the other side. So this term minus this term minus this term equals this term. Our turbine has one flow of mass that is an incompressible fluid that is in a steady flow system. So here's where that mass flow rate is really easy. The mass flow rate has to be equal to the mass flow rate at 0.1, has to be equal to the mass flow rate at 0.2 for these steady flow single stream systems. So therefore we have our Q over time coming out is equal to our mass times our H1 minus H2, mass flow rate times H1 minus H2, because these mass flows are the same, minus our work over time coming out. All right, so in the problem statement, we're given our mass flow rate and we're given energy about work coming out. We're also given information about pressure and temperature at our starting condition, and we're given information about what table to use and the temperature at our final condition. So now we can fix our states and look up these enthalpies. So at 0.1, our pressure at 0.1 and our temperature at 0.1 are equal to 1.6 megapascal and 350 degrees Celsius, respectively. So I think that this is going to be a superheated vapor because it called it steam and it called it saturated vapor in another point. So I think it's going to be that, but we can check that in our tables. So when we go to table A5 and we look up 1.6 megapascal, which is 1600 kilopascal, it's not in here, but we can approximate our Tsat to be about 200 degrees Celsius, which means our temperature is greater than Tsat, which means that we are in fact a superheated vapor. So then when we go to the superheated vapor table at 1.6 megapascal, we have, it tells you in your saturated vapor table that your saturation temperature is 201.37 degrees Celsius. So we are confirmed to be higher than that. Looking at 1.6 megapascal and 350 degrees Celsius, we have an H value of 3,146.0 kilojoules per kilogram. And then for our second point, we know that we have a saturated vapor. So we have our temperature at 0.2 is equal to 30 degrees. We know that this is a saturated vapor, or our quality is 1. So we can go to table A4. So over here, we're at table A6. Now we're going to be in table A4. Good job, Beefy. And we can look up at 30 degrees Celsius, our enthalpy value is 2,555.6 kilojoules per kilogram. And this is our H sub G, right? Because we're a saturated vapor. So that's why I don't have to do my equations or anything. I can just look up my H sub G value. All right, so now I have everything that I need to solve this equation. So Q out is equal to 22 kilograms per second as our mass flow rate, times our H1 value, which is 3,146.0 kilojoules per kilogram, minus our H2 value, which is 2,555.6 kilojoules per kilogram. And this is all going to be subtracted by 12,350 kilojoules per second, or kilowatts, which is the power that's supplied by the turbine. So my kilograms are going to cancel. I'm going to have kilojoules per second minus kilojoules per second. Those units are compatible. So I get about 638.8 kilojoules per second, or 638.8 kilowatts. All right, I don't think I have time to go through the third question that I was going to get through. So that's okay. You have your homework due on Friday, and then you have the quiz to study for, so I don't feel like you're going to be sad about that. Are there any questions about this problem, the quiz, the homework, anything? Can I put the other, sure. I didn't work the solution out yet, so I don't have the solution, but I just pulled it from the back of the chapter. There's the FE problems at the end, and I like the FE problems because number one, it prepares you for the FE, and number two, they're just kind of like short and concise, and they give me multiple choice, so I can kind of check that I haven't made a mistake. So the other one I was going to do is 5-198 in the back of the book. So that's the other one I was going to do. But I haven't worked out the solution or anything.